So here is chapter 5, heat and temperature. In this chapter, you have to know how to convert from one scale of temperature to the other. And that's what the first question is talking about. It's talking about changing minus 20 degrees Celsius into Fahrenheit. And for that, there is a formula that you have to know. This is the formula that changes Celsius into Fahrenheit. So 9 multiplied by negative 20 divided by 5 plus 32. So be careful that you do this part first, which gives you negative 36, and then plus 32 will give you negative 4 Fahrenheit. In the second question, the temperature changes from 50 Fahrenheit at night to 90 Fahrenheit during the day. What's the temperature change on the Celsius scale? Now, this question is important because it's talking about the change in temperature. And on the Fahrenheit scale, the change in temperature is 40 Fahrenheit, right? Change is always final minus the initial. So that gives you 40 Fahrenheit. And from the formula that we wrote on top, let me write that again. So this formula, T in Fahrenheit is 9 by 5 temperature in Celsius plus 32. If you take the change, and you know that the triangle shows the change. If you take the change, and then you will see that this 32 does not count because you're just looking at the change. Another thing is that instead of changing from Celsius to Fahrenheit, this time you're changing from Fahrenheit to Celsius. That's why the formula flips. As you can see here, the change in Celsius is instead of 9 over 5, you have 5 over 9 change in Fahrenheit. So the 32 is gone, and you have the formula flipped because you're changing Fahrenheit into Celsius, and that's all you got to do. Remember that that's applicable only for change. Okay, so when you do that, you get 5 over 9 times the change in Fahrenheit is 40, and that gives you 22.22 Celsius approximately. If you were to consider significant figures, then the answer would only have two sig figures because each of these has only two sig figures. So the answer would be 22 Celsius if you consider the sig figures. Brings us to number 3. How much heat is required to raise the temperature of a 300-gram copper block from 20 to 100 Celsius? So here you have the mass given, the mass of the block. You have the change in temperature given, which is 80 Celsius. And the formula for finding the heat required is Q, that's the quantity of heat, is mass times this constant for copper. It's called the specific heat. Now that constant will be given. You do not have to memorize that. So for copper, it's 385. So you can see that here. So multiply the mass, but it should be in kilogram. That's why I have first changed the gram into kilogram. 1,000 grams make a kilogram, so I have divided it by 1,000. Got the mass in kilogram, so you have that, and then you have the specific heat in proper units, which is joule per kilogram Celsius. And then you have the change in temperature in Celsius. Okay, so when you multiply those numbers, you get the answer as 9,240 joules, which is 9.24 times 10 raised to 3 joules. Number 4, a sphere of surface area A is equal to 2.00 meters squared and emissivity 0.90 is at 150 degrees Celsius. At what rate does it radiate heat into empty space? So this question is about radiation. And we have a long formula for radiation. And the formula for radiation is typically written as Q over T. Now that's heat by time. Now that's also called power. So power is energy over time. Heat is a form of energy. So heat divided by time, quantity of heat divided by time is power. And the formula is you have the emissivity times a constant times the surface area multiplied by the fourth power of the temperature. But the temperature must be in Kelvin. So you have all those quantities there. You have emissivity, which is given. It has no units. This constant is called Stephan's constant, and you have it right there, a really small number. This is not just any area, it is the surface area. Why? Because it is the surface that radiates heat. So here you have a sphere, and it's radiating heat from all over its surface, and the surface area is given in meter square, which is the proper unit. Temperature must be in Kelvin. Remember, this is in Celsius. So the first thing that you have to do is change it into Kelvin. Add 273.15, and you get it as 423 Kelvin approximately. There's no need of 0.15. You can just add 273. So once you get that, plug everything into this formula. But be careful. First, find out T raised to 4, which is 423 raised to 4 in your calculator. You could do that by either finding the square of 423 and then squaring it again, or you could just multiply 423 4 times. I hope that makes sense. And when you do that, you get a pretty big number. So that's just 423 raised to 4. And then after that, you got to multiply that with the emissivity, Stephan's constant, surface area, and that number. So do the math carefully. I've tried to do some combination here. This time, this is 1.8, and then 1.8 times 5.67. It gives you that. And so you can enter everything in your calculator, but just please be careful. You would get this. Okay. And then multiply it with this. So I have done it in parts. When you do all that, you get 3.27 times 10 raised to 3. And the unit is joule per second. Joule per second is also called a watt from the previous chapter. That's the unit of power. Okay, number 5. How much heat must be added to 5 kilogram block of ice at minus 5 degrees Celsius to turn it into water at 10 degrees Celsius? So many times you would think that just when you start heating ice, it would start melting. That's not true. When you heat this block of ice, at first its temperature has to go from -5 to 0 degrees Celsius, which is its melting point. So ice will not melt unless its temperature reaches 0 degrees Celsius. So in this question, there are two parts. Um, so in the first part, the heat required to raise ice from -5 to 0. That is normal heating. That's why we use this formula: mass times specific heat times change in temperature. And that would be the specific heat of ice, because it is ice that's being heated. Again, that will be given. It's about half of that of water, and that's given here. You can see. So you got 5 kilograms of ice. This is the specific heat of ice. And then change in temperature is final, take away the initial. That's why it's 0 minus -5. The two negatives make a positive. So you end up with this, all right? And when you do the math, you would get 51,250 joules. So that's the heat required just to get ice from -5 to 0 degrees Celsius. Next up, if you continue heating, ice is going to melt. But the formula used for any change of phase, PHASE, for melting or for boiling, the formula is different. So you see that? It's just mass times what's called the latent heat. Latent heat. Okay. So again, that constant would be given. So that's 334,000 for ice. So you just multiply it with the mass and you get the amount of heat. And so, oh, there is a third part. I was reading it. See, I didn't read it completely. Look at that. So in the second part, ice has just melted and become water. What is the temperature of water? When ice just melts, uh, water is at 0 degrees Celsius. So what we have is ice at 0 degrees Celsius just became water at 0 degrees Celsius. So in the question, it says you have to take water up to 10. So there is a third part. Okay, so I had said that here, we break the process into 3 steps, but then, okay, so in the third part, you are heating, what are you heating now? Water, because all of the ice is changed to water. So you heating it from 0 to 10. So you go back to the normal formula for heating. See that? Same thing. Except notice, instead of specific heat of ice, you have the specific heat of water, which is 4186. So mass times that times change in temperature is 10, because it's 10 minus 0, you get this number. So you got those 3 steps now. You got to add up all those 3 numbers to get the total amount of heat required, which you can see is quite a large amount. Okay, so that's how you do that question, and that's a very important question. Number 6. This question is about conduction, about heat coming in during summer from outside into the house, or if it's winter, a heat leaving the house through the window to the outside. If you look at this question, can you tell me if it's summer or winter? For sure, you can see that its outside surface is at -5 degrees Celsius. So it's very cold outside. And inside is at 25.0 Celsius. So it's winter. And you have to find the heat flowing through the window in 1 hour. Be careful about this. So how much heat is escaping from the room to the outside in 1 hour? And for that, you're given the thickness of the glass pane. You're given the area, which is length times width. Okay, as you can see here, length times width. That would be the area. And you're also given a constant called thermal conductivity. So that is 1.0 roughly for glass. And then you have the formula. Now, before we go to the formula, what is the temperature difference? be careful here. The temperature difference is the bigger temperature minus the lower. And the two negatives make a positive. So that's why it becomes 30. And then if you look carefully, you would see, hey, but wasn't the unit Celsius? Yes, it was. But why have I written it as Kelvin? Because the change in Celsius will be the same as the change in Kelvin. It will be the same. Okay? Because how do you change from Celsius to Kelvin? You go temperature in Kelvin is temperature in Celsius plus 273. That's how, right? And if you're looking at change, remember from the first or second question, if you do change in Kelvin, is change in Celsius. Why? Because this number cancels out because you're only looking for change. So remember that the change in the Celsius scale is the same as the change in Kelvin scale. That's why I've written it as 30 Kelvin instead of 30 Celsius. Both are correct. At least some students make a mistake there. They will try to add 273. You don't have to do that. Okay, once you got the change in temperature, here is the formula for heat conducted. Q over T, which is power, is the constant times the area times the change temperature by the thickness. Now, the thickness was given in centimeters and also in meter. Okay, you have to use the thickness in meter. So that's the K. You have the area, you have the change in temperature, you have the thickness in meter. Do the math, you get 6,000 watts. But that is the heat lost in 1 second because power means energy or work in 1 second. So automatically we've taken T as 1 second. But the question wants you to find the heat flowing through in 1 hour. And 1 hour is 3,600 seconds. That's why we have to multiply this with 3,600. Okay? Or if you want it more clearly, you can see that here you have Q over T is E, and therefore Q is power multiplied by T, which is what I've done here. Okay? And then you get that answer. 2.16 times 10 raised to 7 joules. All right, bringing us to the seventh question. What's this? Oxygen condenses into liquid at approximately 90 Kelvin. What temperature is this in Fahrenheit? So you just have to change Kelvin into Fahrenheit. Now, there are two steps here. First, you got to change Kelvin into Celsius. And to change Kelvin into Celsius, you subtract 273. Okay? So you get negative 183.15 Celsius. And then you have to use the conversion formula for changing Celsius into Fahrenheit. You might remember that the conversion formula is 9 over 5 temperature in Celsius plus 32, which is what I've used. And so plug it in. Be careful that you do this part first. It's going to be negative, and then plus 32 will give you that. And then if you go by sig figures, there's only two here, so it should have been 300 Fahrenheit. But even if you did not take 0.15, that's okay. So your answer could be negative 298 Fahrenheit or negative 300 Fahrenheit. Doesn't matter. Okay. Eighth one. A person eats a snack containing 10 kilocalories. So be careful on food packets. Although it's written as calories, they mean kilocalories. Okay. So a person eats a snack containing 10 kilocalories and burns it off in 5 hours of exercise. What's the average power output in watts? So first you have to change kilocalorie into joules. So kilocalories, kilo means 1,000. So 10 kilocalories is 10,000 calories because you multiply kilocalorie with 1,000. And then to change calorie into joule, you have to you have to know that one can is 4.186 joules. So that's why I've multiplied with 4.186 to get this. So you got the power, I mean, you got the energy, and now you need the time. Oh, 5 hours, you got to change it into seconds. Since there are 3,600 seconds in an hour, just multiply this and you get 18,000 seconds. So now you have both quantities. Power is energy over time. That's the energy divided by the time. Okay, so in proper units, right? Remember, this is in joules, this is in seconds. So you get 2.326, which is 2.33. All right. Okay. This is about heating a copper rod and it expanding. The expansion is going to be really small. So a copper rod of length 50 centimeter at 25 degrees Celsius is heated to 150. The coefficient of linear expansion, alpha, is given. So that's the constant for copper. What is its new length? So to find the new length, first you have to find the change in length due to heating. So here are the quantities, the initial length, L0, you have the change in temperature, 150 minus 25, and this is the formula for change in length due to heating. So you multiply the original length with the given constant times the change in temperature. Once you get that number, which you have here, or you have it in meters here, and you don't have to change it into millimeter, but this is 0.00103,125 because you move this decimal 3 places to the left. So when you do that, you get that in meter. And since that's the change in length, the new length would be the original length plus the change. So the original length plus the change in meters will give you that, which is approximately 0.5010 meter, right? So you can see that that's a real small change. That's one of the reasons why I put it in millimeter. Look at the change. It's just 1.031 millimeter. That's how small the change is. So that brings us to the last one. This was something like we've done before, but with more steps. How many calories, small c, so that's gram calories, are needed to convert 20 grams of ice at zero into steam at 100? So you're going from ice at zero to steam at 100, and you have 3 steps. We did that before, but it was a little different. So first of all, look at the steps. First, you have to, you know, because ice is at zero, as soon as you start heating, it's going to melt. So first melting of ice, and then you get water at zero. So second step is to heat water from 0 to 100, and then it begins to boil and becomes steam. See that? So those are the 3 steps. And there's only one part where you're heating, which is this part. So you use this formula. This is change of phase from ice to water. This is change of phase from water to steam. Do you see the difference in the formulas? These two are the same, but this is different. So keep that in mind. All the constants are given. The mass has to be in kilograms. So first change it into kilograms, which I did. Divide this by 1,000, becomes kilograms. Multiply with the latent heat of fusion of ice. Second, you have the specific heat of water, which is 4186. So mass times that times change in temperature, 100 minus 0. And the third is mass times latent heat of vaporization. You got that constant here. After you get all that, add all of them up. And since this is in joules, all of this is in joules, but the answer is required to be in calories, you got to change using this. 1 calorie is 4.186 joules. So you divide this by that number, you get it in calories, which is 1.44 times 10 raised to 4 calories approximately. So that is the homework support for chapter 6. Once again, let me know if this is helpful, because by now you know that most of the exam questions are taken with the homework because you have double practice here. That's it from me. We'll see you on the next one. Thank you.